Let's move to the second property now of the free gyroscope, which is known as gyroscopic precession. Now, as we just now discussed, under gyroscopic inertia property, that a free gyroscope is going to resist any attempt to change its direction of spin. However, if we go on increasing the force which is being applied, this resistance cannot match up with the applied force infinitely, and at some point of time, the spin axis will eventually move. To give you an example, let's say we have made a free gyroscope with a cycle tire, and we have imparted it some rotational velocity, and it's moving now. You try to change the direction of its spin axis, it is going to resist any attempt. But let's say you were alone and you were trying to change its direction. It was resisting the attempt. You call your friends. So there are three of you now. Now all three of you try to change its direction of spin. Eventually, at some point of time, you can overpower it. You can overpower its gyroscopic inertia. Now, when you overpower its gyroscopic inertia, it is going to move. The movement of the spin axis, when a force is applied on it and the force is powerful enough to overpower its gyroscopic inertia, this movement of the spin axis is known as gyroscopic precession. So this is the definition of gyroscopic precession. The movement of the spin. We start off with the topic of now a gyro compass basically consists of a gyroscope. It works on the principle of law of conservation of angular momentum, and the gyro compass works by utilizing two natural phenomena to provide us with a directional reference. These two natural phenomena are: one, the Earth's incessant or continuous rotation around its axis. Earth completes one round around its axis in 24 hours. So this rotation of the Earth is utilized to make a gyro compass. And second is the force of gravity. So these are two universal natural phenomena which are there in existence. And in making of a gyro compass, we utilize both these phenomena. So now let us try and simplify and understand all these terms one by one. Now at the heart of a gyro compass is a free gyroscope. So let us first of all understand what do we mean by a free gyroscope. You can see a basic gyroscope in this particular diagram. Now a gyroscope consists of a mass in the form of a wheel or a rotor. As you can see in this particular diagram, this yellow color part which is shown in the diagram, yellow color part is the rotor, and this rotor is suspended or fixed in a special arrangement. You can see that it is suspended in such a way that it is free to spin about an axis passing through its center of mass. You can see there is a brown color rod which is passing through this rotor, and this brown color rod is connected to this blue color ring. Now this brown color rod is connected to the blue ring by way of ball bearings, and these ball bearings allow the rotor to spin about the spin axis. You can see this is mentioned in the diagram also. The rotor can spin around the spin axis clockwise or anti-clockwise because of these ball bearings. Also, you will note that this brown rod or the spin axis is fitted in such a way that it passes through the center of mass of the rotor and is perpendicular to the plane of the rotor. The plane of the rotor is represented by the yellow part, and perpendicular to the plane, you see this brown color rod, which is the spin axis. So exactly as we discussed, as you can see in this diagram, the yellow part is the rotor. The brown rod, which is passing through the center of mass, center of gravity of the rotor, is the spin axis. And this brown rod or the spin axis is connected to the blue horizontal gimbal ring by way of ball bearings. You have a ball bearing fitted at both the ends. This end here shown by the laser pointer and the second end here shown by the laser pointer. These ball bearings provide the freedom to the rotor to spin anti-clockwise or clockwise. Now moving further, if you look carefully at the blue color horizontal ring, you will see that this blue color horizontal ring is connected with the red color vertical ring at two particular points. You can follow the laser pointer. The connection point, one of them is here where the laser pointer is right now. And the second connection point between the blue ring and the red color ring is at this particular point. So the blue horizontal gimbal ring is connected to a vertical red ring through a second set of ball bearings at two particular points. And these 2 points are made in such a way that these are perpendicular to the spin axis. The spin axis brown color rod is here, and you can see the connection point between the blue ring and the red ring are perpendicular to the spin axis. And at these two connection points between the blue ring and the red ring, you have another set of ball bearings. Now this second set of ball bearings, which is present in connection of blue and red rings, they allow or permit the spin axis to move in up and down direction. You see, you can pay your attention to the laser pointer. This end of the spin axis can move upwards. This is known as tilting upwards, or this end can also move downwards. This is known as tilting downwards. So this set of ball bearings connecting the blue and red rings allow the spin axis to move up and down. And this up and down motion is known as the tilting motion. If the spin axis is pointing upwards, we say it is tilted up. And if the spin axis is pointing downwards, we say it is tilted down. Now moving further still, if you pay your attention to the red color vertical ring, you will see that this red color ring is connected to the green outer member. There is a green outer member. The red color ring is connected to the green outer member at 2 points. One point is exactly on top of the diagram. This is 1 point shown by the laser pointer. And the second point where the red ring is connected with the blue outer member is this particular point. Now at these two connection points, we have a third set of ball bearings. So the vertical red ring is connected to a green outer member, and these connection points are at right angles to the spin axis as well as the connection point between the blue and red rings. So right angles to the horizontal axis through a third set of ball bearings. And this set of ball bearings, one fitted on top here, connecting the red ring with the green outer member, and connecting the red vertical ring with the green outer member, they allow the spin axis to move in the horizontal plane. You see, the spin axis can move in the horizontal plane. Looking from top, it can move in the clockwise direction like this in the horizontal plane, or it can move in the anti-clockwise direction in the horizontal plane. So this motion of the spin axis in the horizontal plane, in the plane of the blue color ring, is known as drift or drifting motion. So this third set of ball bearings which we have, they allow the spin axis to drift or turn in the horizontal plane. Now ideally the spin axis bearings, this three set of ball bearings which we have fitted here, one at the ends of the brown rod, second set at the connection point of the blue and red ring, and third set of ball bearings at the connection point of red ring and the green outer member, one on top and one at the bottom. All these ball bearings should be ideally frictionless so that any rotation which is imparted to the rotor is maintained without any loss. However, practically, whenever you impart any motion to the rotor, there will be some amount of friction. Doesn't matter how well lubricated these ball bearings are, there is going to be a small amount of friction. So to counter that, what is done is we put an electric motor on the rotor, just like a normal ceiling fan, and this electric motor maintains a constant RPM on the rotor. So rotor spins with a constant RPM, making this arrangement a free gyroscope. Arrangement. The gyroscope is not constrained in any way so as to alter the direction of its spin axis. It is then said to have 3 degrees of freedom and is called a free gyroscope. So there are 3 degrees of freedom. First freedom is the freedom to spin anti-clockwise or clockwise around the spin axis. You can see this spinning motion shown by this particular arrow. The second freedom is freedom to tilt up and down. The brown color rod can move up and it can move down as shown by the laser pointer. This is known as tilting motion, second degree of freedom. And the third degree of freedom is that this spin axis can move in the horizontal plane, eastwards or westwards. This horizontal plane motion is called as freedom to drift. Combined together, these are known as 3 degrees of freedom. And this particular arrangement is known as a free gyroscope. So a free gyroscope basically has two conditions. One, we should have a rotor and spin axis in this particular arrangement fitted with gimbal rings so that the spin axis is totally free to move in whichever direction it likes. And second, the rotor should be spinning with a constant RPM. Once these two arrangements are made, we have the 3 degrees of freedom and we have the rotor spinning with a constant RPM. This device converts into a free gyroscope, which is the heart of our gyro compass. This 3 degrees of freedom by way of a animation. You can see we have the yellow color part, that is the rotor, and we have the brown rod in the vertical orientation now. The brown rod is the spin axis. The spin axis is connected with 3 outer rings. So you have a ring in the vertical plane, you have a ring in the horizontal plane, and you have an outer member with handles. So this is a free gyroscope having 3 degrees of freedom.
Sir, only the rings are
Now it
rotating.
moves as it likes, and there is no outer force which can be applied to the spin axis if it has this kind of a arrangement. It is shielded from all external forces. So now, having understood a free gyroscope, we can now appreciate the fact that the best example of a free gyroscope in nature is the Earth itself. Earth is the best example of a free gyroscope in nature because it is freely suspended in space having no friction, thus having all the 3 degrees of freedom. There is nothing which is restricting the Earth to change its direct direction of the axis. So it has all the 3 degrees of freedom and can move as it likes. The Earth is heavy and well balanced with the equatorial mass corresponding to the plane of the rotor. Now we know the Earth is slightly flattened at the poles and is bulging at the equator. So the equatorial mass is more as compared to the polar mass. So with this equatorial mass corresponding to the plane of the rotor, it is perpendicular to the axis around which the Earth is rotating. So it corresponds exactly to the rotor and spin axis arrangement which we saw in a free gyroscope. Earth also rotates at a considerably high speed about its axis, which is equivalent to the spin axis of a rotor. The Earth rotates by 360 degrees in a period of 24 hours in one day, which converts to 15 degrees of motion in 1 hour. If you are at the equator, the Earth's rotation covers 15 degrees of d long in 1 hour, and that converts to, at the equator, it converts to 900 miles per hour. 1 minute of longitude is equal to 1 minute of latitude equal to 1 nautical mile at the equator, and the speed at which the Earth is taking a observer who may be present on the equator is a speed of 900 miles per hour or 900 knots. As we move away from the equator and go towards the pole, the speed starts to reduce slightly, but you can check the speed with which the Earth is moving with a formula of 900 cos latitude. So at the equator, 900 knots is the speed. At any other particular latitude, the speed can be calculated by the formula 900 cos of lat. We are now moving into the special properties of a free gyroscope. We know that a free gyroscope consists of a rotor and a spin axis having 3 degrees of freedom. Freedom to spin clockwise or anti-clockwise, freedom to tilt up and down, freedom to drift east and west. Now, as soon as we make a free gyroscope, we have the 3 degrees of freedom and the rotor is imparted some angular velocity. It starts exhibiting two special properties. These are gyroscopic inertia and gyroscopic precession. We are now going to understand these two properties one by one in detail. Now starting with the first property of the free gyroscope, that is gyroscopic inertia. We have the same gimbal arrangement which I showed you earlier. Gyroscopic inertia defines that a freely spinning gyroscope will maintain its axis of spin in the same direction with respect to space, irrespective of how its supporting base is turned, and it resists any attempt to change the direction of its spin axis. Now, as you can see in this particular animation, that the base or the outer member, which is having these two handles attached to it, the supporting base or the outer members as well as the gimbals are turning, but the spin axis maintain its direction. This happens because of gyroscopic inertia. You can move the outer member holding it by these handles in any particular direction you may like, but the spin axis will continue to maintain its direction of spin. Now, very important thing in this property is that the spin axis maintains its direction with respect to space. It is not with respect to the earth, it is with respect to the space. Now, it may not be making much sense at the moment, but later when we go into understanding of the gyro compass, it will become very clear to you what is the significance of this word or this term, that the spin axis maintains the same direction with respect to space. Even if you try to push the brown color spin axis directly, let us say you try to touch the spin axis, the brown color rod, and try to push it manually bypassing these gimbals, the outer member and the gimbals, even then you will feel that it will resist any attempt to change the direction of its spin axis. If it was not spinning and you push the brown color rod, it will move in whichever direction you are pushing it. But as soon as it starts spinning and showing this gyroscopic inertia, even if you push it, it is going to resist any attempt to change its direction. You will see that a resistive force appear, invisible resistive force appear. So thus we can say that a free gyroscope has high directional stability. This is known as gyroscopic inertia or rigidity in space or directional stability. This property can be denoted by any of these terms: gyroscopic inertia, rigidity in space, or directional stability. All three of them mean the same thing. The gyroscopic inertia of a rotor can be quantified. How much is the gyroscopic inertia of a particular rotor? It depends on its angular momentum. The greater the angular momentum of a rotor, the greater will be the gyroscopic inertia exhibit by the gyroscope. The angular momentum depends upon the mass of the rotor and the distribution of the mass. So the quantity, how much gyroscopic inertia is present in a force is applied on it, is known as gyroscopic precession. Now going further in gyroscopic precession, we will try to understand it from diagrams. Now the way in which the spin axis moves is quite surprising. We would expect it to move in the direction of the applied force. That is how normal bodies move. Let us say if you have a chair placed in your room and you push it in a certain direction, the chair is going to move in that direction in which you are pushing it. So we would expect the spin axis to move in the direction of the applied force. But the motion is not in that direction. The motion is at right angles to the applied force. Now, if you talk of right angles, then there will be two directions. If you are applying a particular force, there will be two directions at right angles to the applied force. So in which direction will the spin axis move? It will be at right angles to the applied force in the direction of the spin of the rotor. Now this is a little difficult to understand theoretically. Let's try to understand using a diagram. So you see a rotor here. The rotor is moving in the clockwise direction. If you are looking from this particular side, where you have this arrow, looking from this particular side, the rotor is moving in a clockwise direction. Now, as you can see in the diagram, this arrow represents the force which is being applied. So on this end of the spin axis, we are applying a force in the upward direction. And we would expect the spin axis to move upwards. The spin axis should be moving upwards. But the motion of the spin axis will not be in this particular direction. So a force is being applied to the spin axis, this end of the spin axis, in the upward direction. That means in the vertical plane. But it will be moving in a surprising way. The motion of the spin axis will not be in the vertical plane. The motion of the spin axis will be in the horizontal plane. How will the motion be? The spin axis is not going to move up. What the spin axis is going to do is, see, it is rotating clockwise. So it will move in such a way as if this force has been turned by 90 degrees in the direction of spin. So if it was being applied in this particular way, the rotor is moving clockwise, it will move as if the force has been turned 90 degrees and it is being applied in this particular direction, like this. So you are applying the force in this particular way and the spin axis will move like this. You see this particular arrow being shown here. The force was trying to move the rotor in this particular direction, but it will turn 90 degrees in the direction of spin and the spin axis will move in the horizontal plane. Now, it may be a little difficult to understand from the diagram, so I will be showing you a video later on where it will become more clear to you. We will try to understand it from a different diagram now. Now this diagram, what you see, assume that the spin axis of our rotor is pointing in the north-south direction. So it is pointing in the north-south direction and you are looking at the spin axis and the rotor from the south end. The light blue part which you see here, the blue color part, it represents the rotor of our free gyroscope, and this pink color small circle represents the spin axis. Now the spin axis will be going into the screen. The spin axis which you are seeing will be going into the screen and coming out from the screen towards you. That's how the orientation of the spin axis is. And since you are looking at it from the south end, we have represented it by letter S. So this is the south end of the spin axis. And the rotor is spinning in this particular direction. That means looking from the south end, it is spinning anti-clockwise. So this curved black arrow gives us the direction of spin of the rotor. Now let's imagine that we apply a force and we apply it to the south end of the spin axis. This blue color arrow which you see here is the force or torque being applied to the south end of the spin axis. Now if this was a normal object, the spin axis will move in this direction only. In the direction of the blue arrow, it will move in this same direction only if it was a normal object. But since this is a free gyroscope, it is not going to move in this particular direction. It will move at right angles to the applied force. Now there are two directions at right angles to the applied force. One is upwards, another is downwards. So which direction is it going to move? This is decided by the direction of spin. You see the direction of spin in this case, looking from the south end, is anti-clockwise. So the spin axis is going to move in such a way as if the force has been turned by 90 degrees in the direction of spin. If you turn it by 90 degrees in the direction of spin, the force will be applied upwards. And this is how the spin axis, the south end of the spin axis, is going to move. So you see the red color arrow shows us the direction of motion of the south end of the spin axis, and this is the direction of precession. So the blue arrow in the diagram is the torque applied to the south end of the spin axis, and the red color arrow or the brown arrow shows the direction in which it will precess. So the south end of the spin axis is going to precess upwards. As you can see, the motion occurs as if the applied force has been turned by 90 degrees in the direction of the spin. So I hope this diagram has given you more clarity now into what precession is. Now this looks very surprising. You are applying a force in the horizontal plane and the spin axis is moving in the vertical plane. In normal physics, any vector which you apply at right angles to that vector, there is no effect of that particular force. But in this condition, the vector is being applied, the force is being applied in the horizontal plane, and the south end of the spin axis is moving in the vertical plane. That's surprising, but that's the property of a free gyroscope. See what will happen if the direction of spin in this case was clockwise. So rest everything we will keep same. Only thing what we are going to do is we are going to change the direction of spin to clockwise. So you see the blue color disc which we have, it represents the rotor of the free gyroscope. The pink color circle which you see in the center is representing the spin axis. The spin axis is going into the screen and coming out of the screen, pointing in the north-south direction, which means the screen which you are seeing, that is the northerly direction, and you are sitting south of the screen. So the direction of spin in this case is reversed. You see the direction of spin is clockwise. So the force which is being applied is the same. We are applying the same force now. Now in this particular case, when you apply the force in the horizontal plane, it is going to turn by 90 degrees in the direction of spin. So this blue color vector is going to spin 90 degrees clockwise. Now once it spins 90-degree clockwise, it will be pushing the spin axis vertically downwards. And that is how the spin axis is going to move. The same force
Sir,
being
what
applied
info?
now results in the spin axis precessing downwards, as if the applied force has been turned by 90 degrees in the direction of the spin. So blue color vector shows the force applied. The red or brown color vector shows the direction of precession of the spin axis. Gyroscope. First one was gyroscopic inertia and the second one was gyroscopic precession. Let me show you one video. Just give me a minute.
This is an egg chop production, and we're going to demonstrate a gyroscope spinning. Now, over here we have a brass gyroscope, toy gyroscope. There's this brass flywheel that rotates in this axis, and it's on a gimbal. And the gimbal is made to spin around this axis, and also on a vertical axis this way. Now, what I'm about to do is spin this gyroscope using a Dremel with a little rubber wheel on this, and I can get this to spin about anywhere between 3,000 to 6,000 revolutions per minute.
Beta, are you?
And wants to resist movement. As a matter of fact, it's going to prevent me from trying to move it in this axis. So here we go. I'm going to start this gyroscope spinning. Again, clockwise from your motion going like this. I also put some spiral marking on the flywheel so you can see that the gyroscope will be moving. All right, here we go. There we go. Now the gyroscope is spinning about 3000 RPM in this axis. And as you can see, if we try spinning this gyroscope around this axis, it's going to want to resist movement. Here we go. Let's see what this gyroscope wants to do if we try to spin it in this axis. There we go. I'm going to try pushing the gyroscope the other way, pushing the right hand side of the gyroscope towards you, and you're going to see what it's going to want to do. There we go. Now, if I orient this gyroscope so it's spinning
So beta, are you able?
up and down, it's going to be very easy to spin it. There we go. But only in that direction. If it becomes dislodged from that direction, it's going to want to resist. There we go. It's going to be very hard to spin it. As you can see my fingers are trying to apply some force, spinning it. And it's very difficult to try to spin it with the gyroscope moving at that speed. Once the
So beta clockwise or anti-clockwise direction. This is known as the spinning motion. It is spinning. The rotor is spinning. Okay, this is one freedom.
Axis, and it's on a gimbal, and the gimbal is made to spin around this axis.
This motion beta, what he is doing with his hands, let me mute him and I'll speak to you. So just give me a minute. I'll explain that again. So this motion which he is doing with his hands now, he is spinning the spin axis clockwise or anti-clockwise. This is called as spinning motion. Spinning motion. This motion in which the spin axis is going up and down, it's called as tilting motion. Tilting up, tilting down. And this motion in which the spin axis is moving in the horizontal plane is called as drifting motion. So are the three types of motion clear, beta? Let us say like this.
Okay.
It gets turned in the direction of spin by 90 degrees and the rotor starts to move upwards. OK, I apply a force like this. It gets turned 90 degrees in the direction of spin. The rotor spins or tilts upwards. I apply a force like this. The rotor tilts upwards like this. This is precession. Clear, beta?
Yes, sir. Clear.
Great.
So it means before you're applying the force, the spin axis is already moving in the clockwise direction, right? Sir?
That's right, beta. I apply the force. The spin axis moves upwards.
Okay, sir. It means before we applying the force, it is already been on the clockwise motion, the spin axis.
Yeah, motion is already there, beta. Then only
Okay.
it will become a free gyro.
Okay, sir. Understand. Okay.
Okay. Okay, beta.
So basically, we are applying a force on the spin axis, and spin axis gets tilted, and the direction of the precision remains same, like the rotor was rotating. So we can visualize with that video or this disc that in which direction it is moving, and after tilting means when we are applying the force on the spin axis, in which direction spin axis gets turned, and in which direction the rotor is moving. So we can see the Uh,
So can you see the motion of the stars, beta?
Yes, sir.
Very good. You see a star which is there, it is not moving at all. It is there in the center here somewhere. Can you tell me which star is this which is not moving?
Pole star. North Star.
Very good. That is the pole star, the Polaris. You motion of the stars. Now we have understood a free gyro. What is a free gyro? And we have understood its two properties of gyroscopic inertia and gyroscopic precession. Also, we have seen the motion of the stars in the sky. We know how the stars appear to move in the sky because of the rotation of the Earth. Now, what you see on the screen is a still picture of the sky showing a time-lapse picture of the sky showing the motion of the star. So you see all these concentric circles representing different stars, and all these concentric circles are centered at a particular point, and this point which you see at the center is the pole. Now with these things clear in our mind, we are now going to understand how is the spin axis of a free gyro going to behave or going to move with respect to the Earth surface. So let's try to understand that. So first thing, the center of all these concentric circles is the pole. We are aware all the stars, they move in concentric circles, which are basically their declination circles around the pole. So let us mark the center of all these circles as the pole. Now this picture is taken on land. This is basically the camera pointing towards the North Pole, capturing the horizon as well as the motion of the stars. It is a time-lapse picture of the motion of the stars. So because it is taken on land, the horizon is not very clear. So let's mark the horizon in this diagram. You can see this blue color line appearing at the bottom. This represents the horizon of the observer. So this is the horizon. Now let's assume that we have a free gyro and we want to have a gyro compass which can give us a direction reference. Now we want our free gyro spin axis to point towards north. So let's first identify the north point on our horizon. Now if we come vertically down from the pole, the point where it touches the horizon, that is the north point of our horizon, of the observer's horizon. So you can see this yellow color vertical line passing from the pole. Wherever this line touches the horizon at this particular point, this is the north point of our horizon. So we want our spin axis to point to north. Now, if we go to this vertical line, the yellow color line which we see, basically represents the meridian of the observer. So let's mark this line as the meridian. This represents the meridian of the observer. The meridian passes from the pole. Now, if N is the point representing the north direction, if we go towards the right hand side, this represents the easterly direction. So you see the easterly direction coming up on the right side of the diagram. And from point N, if we go towards the left hand side in this particular direction, this represents the west direction. So east and west also identified in the diagram. Now let's assume we have a free gyro and we want to make a gyro compass with it, and we align the spin axis of that free gyro to the north point on our horizon. Beta, up to here, any doubt coming to your mind? horizon. So I point the spin axis of my free gyro to this endpoint. Now, if my gyro spin axis is pointing towards this particular point, the end point in the diagram, November point, that means my gyro star is also going to be here. So you can see the gyro star in the diagram now. We have shown the gyro star at particular point N. Now we have the gyro star. We can also show the motion of the gyro star. We know all the stars will be moving on concentric circles around the pole, and they will be moving in an anti-clockwise direction. A gyrostar is basically any imaginary star in the direction of our spin axis. You the declination circle of the gyrostar. So you can see this declination circle of the gyrostar, the yellow color circle. The arrow represents the direction in which the star will be moving. So this is the declination circle on which our gyrostar will be moving. Now, once we leave our spin axis pointing towards the November point or towards this particular gyrostar, after this, the gyrostar is going to move on its declination circle. And after about approximately 6 hours, this is where you will have the gyrostar. You can see it represented by point A in the diagram. So after 6 hours, our gyrostar is going to be at this particular location. After this, it is going to move further on its declination circle, again shown by the arrow, the yellow color arrow on its declination circle. And after about 12 hours, the gyrostar is going to be at this particular location. This is point Bravo. The gyrostar is going to reach at this particular location after 12 hours. So from point Bravo, the gyrostar is going to move further on its declination circle, again shown by the yellow color arrow. And after about 18 hours, the gyrostar is going to be at point Charlie, point C in our diagram. This is where the location is. This is the position where the gyrostar will be after 18 hours. And if we keep on observing it further, it will again move on its declination circle, and after 24 hours, it is going to come back at point November. So beta, doubts up to here? Of the gyrostar covered in 24 hours, and it has come back to November, and day after day our gyrostar will keep on repeating this motion. Now if our gyrostar is making this kind of a motion, because of gyroscopic inertia, the spin axis is also going to follow the gyrostar. So when you set it at point November, after 6 hours, as the gyrostar comes to point alpha, our spin axis is also going to point towards point alpha, position alpha. Now, if you look carefully, the motion of the gyrostar between November to alpha, the gyrostar is increasing its altitude. That means the spin axis tilt is also increasing in value. So gyrostar increasing its altitude, the spin axis tilt is exactly same as the altitude of the gyrostar. So the tilt of the spin axis will also be increasing, or you can say the spin axis will be tilting upwards. From November to alpha, the spin axis will be tilting upwards. You can see this coming up here. The tilting of the spin axis will be upwards. The second thing which we note, when the gyrostar is going from November to alpha, it is changing its azimuth in the easterly direction. At point November, the azimuth was 0, 0, 0, and as it moves towards point alpha, the azimuth is moving or changing in the easterly direction. The star is moving towards easterly direction. Now the azimuth of the gyrostar represents or refers to the drift of the spin axis. Spin axis will also be drifting in the same direction, that is the easterly direction. So from November to alpha, the spin axis will be tilting upwards, and it will be drifting in the easterly direction. So this motion is going to take 6 hours. After 6 hours, our gyro star is going to move from point alpha to point Bravo. Any doubts? The gyro star is moving from alpha to Bravo. Its altitude is still increasing. So the gyro star is moving upwards in the sky. So the tilt of the spin axis will also be increasing. So it will also be tilting upwards from point alpha to point Bravo between 6 to 12 hours. The spin axis of the free gyro will be tilting upwards. You can see this coming up in the diagram. And the second thing which you notice, when the gyro star is moving from point alpha to point Bravo, it is moving in the westerly direction now. See, the left side in the diagram is the westerly direction, and star's azimuth is now moving in the westerly direction. So the spin axis will also be drifting westerly. Clear, beta?
Yes, sir.
Point Bravo, the gyro star is going to move from Bravo to Charlie. When it is moving from Bravo to Charlie, you can now observe that the altitude of the gyro star is decreasing. The altitude is decreasing. It is coming down in the sky. So that tells us that the tilt of the spin axis will also be decreasing. The spin axis will also be moving downwards. So we can say that the spin axis is tilting down. And another thing which we notice, when the gyro star is moving from Bravo to Charlie, it is moving in the westerly direction. It is moving towards the left side in the diagram, and the left side represents the westerly direction. So that tells us that the drift of the spin axis will also be changing in the westerly direction, or you can say the spin axis will be drifting westerly. The drift of the spin axis basically refers to or corresponds with the azimuth of the star. So azimuth moving westerly, the spin axis is also drifting westerly. Now moving from Charlie to November, you can see the gyro star is decreasing its altitude. The altitude of the gyro star is decreasing, or it is moving downwards in the sky. So that tells us that the spin axis will be tilting down. So you can see it coming up. Spin axis will be tilting down. Also, if you notice, from point Charlie to point November, the star's azimuth or star's direction is now, it is moving in the easterly direction. It is moving towards the right side of the diagram. The right side of the diagram is the easterly direction. So the drifting of the spin axis will be easterly. So to summarize, from November to alpha, tilting will be upwards, drifting will be easterly. Alpha to Bravo, tilting will be upwards, drifting will be westerly. From Bravo to Charlie, tilting will be downwards, drifting will be westerly. And from Charlie to November, tilting will be downwards and drifting will be easterly. Our spin axis is going to follow this particular motion of the star day after day, completing one oscillation or one round in 24 hours or in one day. The vertical yellow color line which we have represents the meridian of the observer. And if you watch carefully, whenever the gyro star is east of the meridian, that is from point November to point Alpha to point Bravo, this semicircle is east of the meridian. Right side is the easterly direction. Whenever the gyro star is east of the meridian, you see it is always moving upwards in the sky, or its altitude is always increasing. So this tells us that the tilting of the spin axis will be always upwards east of the meridian. And if you look carefully after Bravo, the gyrostar goes west of the meridian from Bravo up to Charlie and then up to November. Bravo to Charlie to November, this semicircle is made to the west of the meridian. And whenever the gyrostar is west of the meridian, you can see its altitude will always be decreasing. If the altitude is decreasing, this tells us that the tilting will always be downwards west of the meridian. So the spin axis tilting will be downwards west of the meridian, and spin axis tilting will be upwards east of the meridian. The second important thing to note is we have the pole in this diagram at the center of the declination circle. Now let's draw a line showing the altitude of the pole. You see this green color line here in the diagram. This green color line basically shows all the points at the same altitude at the pole. Now if you look carefully, whenever the gyrostar is above this green color line, it is moving in the westerly direction. You see from Alpha to Bravo, it is moving in the westerly direction. Westerly direction is the left side in the diagram. So from Alpha to Bravo, it is moving westerly. From Bravo to Charlie, it is again moving in the westerly direction. So this tells us that the drifting of the spin axis is going to be westerly from Alpha to Bravo to Charlie. And if you look carefully, this semicircle Alpha to Bravo to Charlie is when the gyrostar is above the pole. Whenever the star is above this green color line, it is said to be above the pole, or in other words, its altitude is higher than the altitude of the pole. And whenever the star is below this green color line, it is said to be below the pole, which means the altitude of the gyrostar is less than the altitude of the pole. So we come to a conclusion here. Whenever the gyrostar or spin axis is above the pole, the drifting is going to be westerly, and it is happening from Alpha to Bravo to Charlie. Now once the gyrostar crosses Charlie, it comes below the pole, and you see when it crosses from Charlie going towards November, it is moving in the easterly direction. Also from November to Alpha, it is moving in the easterly direction. So whenever the gyrostar is below the pole or its altitude is less than the altitude of the pole, it will be moving eastwards. So that tells us that whenever the spin axis is pointing below the pole, the drifting will be easterly. So from Charlie to November to Alpha, the drifting is easterly. Now these are very important to understand the making of a or converting of a free gyro into a gyro compass. Once we know these directions, it makes it very easy to understand how a free gyro is converted into a gyro compass. Now moving further in our explanation, we have seen the tilting and the drifting motion of the spin axis. As the altitude and azimuth of the gyrostar changes, it keeps on tilting upwards or downwards, it keeps on drifting eastwards or westwards. Now, we have formulas which are available to us with which we can find what is the rate at which the spin axis is going upwards or coming downwards. And we can also find out what is the rate at which it is moving in the easterly direction or westerly direction. So what is the magnitude of tilting, or how fast is the spin axis going up or down? And what is the magnitude of drifting, or how fast the spin axis is going easterly or westerly, can be found using formula which we will see one by one. We now move into the detail of tilt and how to calculate the tilting using a formula. Tilt is the angle of elevation or depression of the spin axis above or below the horizontal, equivalent to the true altitude of the gyro star. The rate of change of tilt of the spin axis is known as tilting. In short, it is known as capital T small g, Tg, and it can be calculated by using the formula. The formula is tilting is equal to 15 degrees sine of azimuth multiplied by cos of latitude per hour. So azimuth is basically the azimuth of the gyro star at any particular instant, or the azimuth, or you can say the drift of the spin axis, and the latitude is the latitude of the observer or wherever the gyro is placed. And this value which we will obtain is basically the rate of change of tilt or tilting per hour. So in 1 hour, the tilt is going to change by this much of a value. The azimuth which is used in the formula is used in the quadrantal notation, not in the three-figure notation. And the formula gives us the magnitude of tilting. How do we obtain the direction of tilting? We know that tilting will be upwards or positive if spin axis or gyro star is east of the meridian. We have seen in this particular diagram, whenever the gyro star is east of the meridian, the tilting is always upwards. And whenever the gyro star is west of the meridian, that is from Bravo to Charlie to November, the tilting is always downwards or negative. So tilting will be upwards or positive if spin axis or gyro star is east of the meridian, and tilting will be downwards or negative if the spin axis or gyro star is west of the meridian. Formula and will help us in understanding converting a free gyro into a gyro compass. On to understanding of the drift and the drifting formula. Drift is the direction in which the spin axis points with respect to the true north. It refers to the azimuth of the gyro star. Whatever is the azimuth of the gyro star, same will be the drift of the spin axis. The rate of change of drift is known as drifting. In short, capital D and small g, dg, is represented as drifting. Now drifting can be calculated using the formula. Drifting is equal to 15 degrees sine of latitude per hour. Now the formula is going to give us the magnitude of drifting. That means in 1 hour, how much is the azimuth of the gyro star going to change, or how much is the drift or direction of the spin axis going to change. How to find out the direction of drifting? We have already seen this in the diagram. The drifting is easterly or positive if the spin axis or gyro star is below the pole. As you can see in this diagram, from point Charlie to point November to point Alpha, in this semicircle, the gyro star or the spin axis is below the pole. The height of the pole is represented by the green line, and whenever it is below the pole, the drifting is easterly. It is also considered as positive, a sign convention which we use. And the drifting is westerly or negative if the spin axis or gyro star is above the pole. As you can see from point Alpha to point Bravo up to point Charlie. In this semicircle A to B to C, the gyro star or the spin axis is above the pole, above the green color line, and in this case the drifting or the motion of the star is in the westerly direction. So this westerly drifting as per sign convention is named as negative, or is referred to as negative drifting. Now, not required in the understanding of the gyro compass, but just for your information, this formula seems to be very simple. Drifting given by 15 degrees sine of latitude per hour. Now there is one restriction or limitation of this formula. This formula is only applicable if the spin axis is almost horizontal or the tilt is close to 0 or the spin axis is pointing close to the horizon. But in our case, this limitation does not affect us. It is appropriate for gyro compass because the gyro compass is designed in such a way that the spin axis always remains close to the horizon. So we will not be or cannot use this formula to find the drifting of the star throughout its motion, but it is appropriate for us for the purpose of a gyro compass. Step of conversion is controlling the gyro, and that is done using a top heavy or a bottom heavy control. Now for controlling the free gyro, we use the force of gravity. The force of gravity is used to control the circular motion of a free gyro using two different effects. These effects are known as the top heavy effect and the bottom heavy effect. We will discuss these effects one by one. The top heavy effect is used if the rotor is spinning in anti-clockwise direction, and the bottom heavy effect is used with clockwise spin of the rotor when viewed from the south end of the spin axis. Let's now try to understand the top heavy control in a gyro. Till now we have seen the spin axis and rotor being fitted in an arrangement of gimbals to give it 3 degrees of freedom, sets of ball bearings, gimbal rings, which give them 3 degrees of freedom. Now we introduce one more part of the gyro compass, and that part is the casing. So as you see in this diagram, you see the light blue part shown in the diagram is basically the rotor as well as the spin axis. The north and south points represent the north and south ends of the spin axis, and this light blue part in the middle represents the rotor. It is the side profile of the rotor. Now outside the rotor you see a black color casing. This is called as the rotor casing. Till now we have not seen the rotor casing in any of the gyro diagrams, but actually when the gyro compass is made, this rotor and spin axis arrangement is fitted inside a rotor casing. Now how is it fitted inside the rotor casing? We have to give it freedom to spin. So for that purpose, you see these dark blue parts which are shown here at the north end and at the south end, they represent ball bearings. So the spin axis is connected with the casing through these ball bearings, thus giving it freedom to spin. The casing, black color casing which you see in the diagram, is not free to spin. Only the rotor and spin axis inside the casing is free to spin. So the casing does not spin at all. However, the casing is free to tilt up and down. The casing is also free to drift east and west. Only freedom which is not available to the casing is the freedom to spin, and that freedom is provided to the rotor and spin axis through these dark blue ball bearings fitted at north and south ends of the spin axis. Now the gyroscope is made or controlled to point in one direction by attaching a weight on top of the casing. You can see this red color weight which is fitted on top of the casing. You can consider it is welded on top of the casing, and this weight is approximately close to 680 grams. The Sperry Maker Mark 20 gyro, this is one particular model of the gyro compass which is very frequently used. They use this casing for 600, they use this weight for 680 grams. This weight is fitted exactly on top of the rotor casing, and it is exactly on top of the center of gravity of the spin axis and the rotor system. So the weight is fitted on the rotor casing exactly above the center of gravity of the spin axis and rotor system. The top heavy weight in this orientation looking from the side. Now in this case we are looking from the side at the rotor casing. We see the top heavy weight, red color weight on top. And this is exactly what you see on the right side of the diagram. This particular orientation, you are looking from the side of the rotor and the casing. Now, if you visualize looking at this particular arrangement from the south end, you can see this eye here, and this is looking at this particular arrangement from the south end. If you look at this arrangement from the south end, the arrangement would look like this particular diagram. The point here which you see is the south end. Then you see this is the rotor, and the outer black color lining which you see represents the rotor casing, and we have the top heavy weight right on top, the red color weight. And if you look at this particular arrangement from top, you see looking from top, you have the eye placed here, and you are having a bird's eye view looking from top of the arrangement. Then this arrangement is going to look like what you see in this particular diagram, looking from top. You will be able to see the flat portion of the casing, and you will be able to see the top heavy weight exactly in the center. This is the spin axis. So this is the view, just to give you a better idea about the orientation of the rotor, the casing, and the top heavy weight. This is horizontal. The center of gravity of the attached weight is exactly in line with the center of gravity of the rotor, thus producing no torque at all. However, we know that our spin axis follows the gyrostar, and as time passes, the gyrostar is going to move, and as the gyrostar moves, the spin axis is going to follow it, and soon it will have some upward tilt and an easterly drift. Now please take your attention to this diagram on top. As soon as the gyro spin axis tilts upwards, you can now clearly see that the center of gravity of the weight does not act through the center of gravity of the rotor. And this weight now produces a torque in the vertical plane. And as you can see in this diagram, the torque is going to result in precession. And how is this precession going to act? Take your attention to the bottommost diagram. This is looking at the rotor and spin axis arrangement from the south end. Now you can see that the weight is now acting on the south end, pushing it downwards. This is represented by the blue color arrow in the bottom diagram. You can see the blue color arrow showing the torque which is being generated by the top heavy weight. Now when this weight acts on the spin axis, because of precession, this torque turns 90 degrees in the direction of the spin. Now we know top heavy control is used in gyro compasses which are spinning anti-clockwise as viewed from the south end. So you can see the direction of spin as anti-clockwise. So this torque which is trying to push the spin axis downwards turns by 90 degrees in the anti-clockwise direction, and now it tries to push the spin axis or precess the spin axis in the easterly direction. So the torque is resulting in a precession in the horizontal plane that tends to take the south end in the eastward direction. If the south end is pushed in the eastward direction or south end is precessed in the eastward direction, the north end is going to precess westwards. Now, when the north end precesses westwards, it is going back towards the meridian. If you remember the motion of the star was drifting in the or changing its azimuth in the easterly direction and it was tilting upwards. The star was trying to go east of the meridian. Now, because of this precession, the north end of the spin axis precesses towards the meridian. So you can see we have now generated a force which opposes the eastward motion of the north end of the spin axis. Repeating once again, as soon as the gyro star has an easterly drift and an upward tilt, this top heavy weight generates a torque which tries to push the south end downwards. Because of precession, this downward torque is rotated in the anti-clockwise direction by 90 degrees and tries to move or precess the south end eastwards, which results in the north end precessing westwards. And when the north end precesses westwards or moves towards the west, it is moving back towards the meridian. Or in other words, you can say the easterly motion of the spin axis is now checked or controlled by this top heavy arrangement. This precession is known as control precession and in short known as PC, capital P with a small c. In this diagram, you can see the horizon. The horizontal black line represents the horizon and the vertical black line represents the meridian. Initially, our spin axis was pointing towards the horizon in the meridian, that means with zero tilt and zero drift. Now we are aware that after some time the gyro star is going to move eastwards and it is going to have a positive altitude. So our spin axis is also going to have easterly motion, easterly drifting, and it is going to have an upward tilt. So this blue color track shows the motion of the gyro star and which is being followed by the north end of the spin axis. Now, as the gyro star has some positive true altitude or the spin axis has some upward tilt, this control precession comes into the picture. And because of this control precession, you see the weight is, as soon as the spin axis is tilted, the weight is no more directly above the COG of the rotor. It tries to push the south end downwards. You can have a look here. The red arrow represents the torque affecting on the south end of the spin axis. And since it is moving anti-clockwise, it generates a easterly precession of the south end of the spin axis. With the south end precessing in the easterly direction, the north end has to precess in the westerly direction. The green arrow shows the direction of precession or direction of the force which is generated, and you can see that this is opposing the motion of the free gyro, the eastward motion of the free gyro, and it is taking the spin axis back towards the meridian. Now some important points to keep in mind. Number one, the control precession PC which is generated is directly proportional to tilt. When the tilt was zero, that means in this particular condition, the spin axis was perfectly horizontal. The center of gravity of the weight was directly over and above the COG of the rotor. So it was not generating any torque at all. So the control precession was also zero. Now, as soon as some tilt is generated, the weight starts to act on the south end of the spin axis, generating a precession, trying to take the spin axis back towards the meridian. Now, you can easily visualize that as the tilt of the spin axis increases more and more, the difference between the weight acting downwards and the center of gravity of the rotor is also going to increase more and more. So the lever is becoming more and more as the tilt increases, telling us that the control precession which is generated is directly proportional to tilt. This is a very important relationship which we will be using in our further understanding of the gyro compass. If the north hand is tilted upwards, the precession caused is westerly. You can easily see from these diagrams, spin axis was horizontal here. There was no torque which was being generated because of the top heavy weight. Now in this diagram, you see a upward tilt of the north end of the spin axis, the weight acting downwards on the south end. And if you come back to this diagram now, weight acting downwards on the south end generates a easterly precession in the south end of the spin axis, and at the same time generates a westerly precession in the north end of the spin axis. Now we can easily understand that in a case if the north end is tilted downwards, the precession generated will also be exactly opposite, and in this case the precession which is generated will be easterly. When the north end is tilted upwards, a westerly precession is generated, and when the north end is tilted downward, a easterly precession is generated. So as we can see in this diagram, the westerly precession which is generated in this particular case is going to oppose the easterly motion of the free gyro, thus trying to keep in or bring it back towards the meridian. Now looking at this diagram, it becomes very easy to understand that why this top heavy control is used in the gyros which are spinning anti-clockwise. The reason is that the direction of spin of the rotor must be such so as to produce a westerly precession of the north end of the spin axis when that end is tilted upwards. Because we know the motion of the gyrostar is such that it moves in the easterly direction and it has a positive altitude. That means the spin axis is moving easterly or drifting easterly and is having an upward tilt. So we want to generate a force which creates a westerly precession when tilted upwards. When the spin axis is tilted upwards, it should generate a westerly precession, bringing the spin axis back to the meridian. So this is exactly the reason. You can see in this diagram also that if the torque is pointing downwards in the southerly direction, you have a anti-clockwise spin of the rotor. This torque generates a easterly precession on the south end and a westerly precession on the north end of the spin axis. Now if the gyro was spinning clockwise, in case of a clockwise spin, the precession generated at the south end would be westerly, and the precession generated at the north end of the spin axis would be easterly, thus taking the spin axis farther away from the meridian, defeating the whole purpose. Now when we go to bottom heavy type gyros, we will see that in bottom heavy type gyros, the spin direction needs to be clockwise for generating the exact same effect. Now let's have a look at a bottom heavy arrangement in a gyro which is spinning clockwise. You have a similar diagram here, the only difference being that this weight is now attached at the bottom of the casing. You can see the spin axis, two ends of the spin axis represented by N and S. You can see the rotor in the middle. The black outline represents the rotor casing, and this red color weight is attached to the bottom now. Now we know after some time the gyro star is going to move eastwards and have a positive altitude, upward altitude. So the spin axis, the north end of the spin axis is also going to have a upward tilt. Now have a look at this particular diagram, the right side diagram on top. You see as the spin axis, north end of the spin axis tilts upwards, this weight which is fitted at the bottom of the casing tries to make it vertical again. Now when it tries to make it vertical again, it is basically trying to push the south end upwards or the north end downwards. So because of gravity, this red color weight which we have fitted is trying to make the spin axis horizontal again, and due to this it is trying to push the south end upwards and the north end downwards. Now you can have a look at the bottommost diagram. This is the south end of the spin axis where the laser pointer is right now. The weight is trying to push it upwards. The rotor has a clockwise spin. Because of the clockwise spin, the precession which is generated is in the easterly direction. The south end of the spin axis precesses in the easterly direction, and this results in the north end of the spin axis precessing in the westerly direction. So again generating a similar effect, taking the spin axis north end back towards the meridian. So if the gyro is spinning clockwise, the weight has to be fitted at the bottom to generate the similar effect. By spinning gyro, as the north end of the spin axis tilts upwards, the bottom weight generates a torque to bring it down. With the spin being clockwise, this torque is converted into a westerly precession of the north end, taking it back towards the meridian. So irrespective of whether we have a anti-clockwise spinning gyro with a top heavy arrangement or a clockwise spinning gyro with a bottom heavy arrangement, in both the cases, similar effect can be generated. So a very important takeaway from this discussion now, the control precession which comes into the picture now because of the weight which we have fitted, top heavy or bottom heavy, this control precession represented by PC is directly proportional to tilt. When the tilt is 0, the control precession is 0. As the tilt starts to increase, the control precession also increases. It is directly proportional to tilt. So this tells us about the magnitude of the control precession. Now the direction of the control precession, whenever the tilt is up, the control precession which is generated is westerly. We have seen that in these two diagrams just now. The spin axis was tilted upwards and it generated a westerly precession of the north end of the spin axis. Now whenever the spin axis is tilted down, though we have not seen it till now, but in case the spin axis is tilted down, the control precession which will be generated at the north end of the spin axis will be easterly. So whenever we refer to the direction of the precession, it is always of the north end, as we are interested in the north end of the spin axis. We are not interested in the south end of the spin axis. So remember, when the tilt is up, the control precession is westerly, and when the tilt is down, the control precession is easterly. This is a very important relationship for understanding the gyro fundamental. So when we proceed ahead and we try to understand the motion of the gyro, we will be using these expressions. So keep it in your mind. So clear beta up to here? So in which the spin axis was following the motion of the gyro star. the spin axis was moving in a circular fashion. You can see this blue color circle in the diagram. This represents the path traced out by the spin axis of a free gyro. The center of the circle was the pole. The gyro star was moving in circles around the pole and the spin axis was following that motion, completing one circle in one sidereal day or 24 sidereal hours. It was only under the effect of two forces. These were tilting and drifting. Tilting was caused because of the change in altitude of the gyro star. Drifting was caused because of the change in azimuth of the gyro star. Now we have introduced a third force in the picture, and that third force which is introduced is the control precession using a top heavy arrangement or a bottom heavy arrangement. Now the path of the controlled gyro converts to a elliptical path. This red color ellipse which you see at the bottom of the diagram is the path which is now traced out by the controlled gyro. Another important thing, you can see that the path has become very much smaller and shorter than before. Another important thing, this path is now traced out by a gravity controlled gyro. This is called as a gravity controlled gyro in 84 minutes. The blue circle was being traced in 24 hours, whereas the red elliptical path is being traced out in 84 minutes.
Sir, it will come.
So the gravity controlled gyro now traces the red elliptical path under the effect of three forces or three factors, which are tilting, caused because of change in altitude of the gyro star, drifting, caused because of change in azimuth of the gyro star, and control precession, which is caused because of the top heavy or bottom heavy arrangement which we have fitted. The control precession is generated by the top heavy or bottom heavy effect, and its introduction results in the spin axis tracing an elliptical path. The circular path was being completed in one sidereal day, whereas the ellipse oscillation is covered in approximately 84 minutes. The important thing to note here is that the entire ellipse is now formed below the pole, as the pole is situated at the center of the blue circle. Now, if you go back to the free gyro, you will remember that this blue color path which the free gyro was tracing was following the motion of the gyro star, and this motion was centered at the pole. So at the center of this blue circle is the pole here, where you have the vertical and horizontal line meeting. Very important thing to note here, which we will be using later in the explanation of gyro, is that the elliptical path which is formed now by a controlled gyro, traced by a controlled gyro, the entire ellipse is below the pole. At no point on the ellipse you see the spin axis going above the pole. The spin axis always remains below the pole. So this will be used later on when we understand the elliptical motion in detail. So what have we achieved by controlling the gyro? In this gravity controlled gyroscope, we have been able to restrict the circular motion of the spin axis to a much shorter ellipse. You can see now that the spin axis is much closer or remains much closer to the meridian as compared to the free gyro, which was moving large distances away to east as well as to the west of the meridian. Now after this, next we are going to discuss and analyze the elliptical motion in detail, understanding the behavior of the controlled gyro. Now, even now, when the gyro is moving on an elliptical path, which is much shorter as compared to the circular path traced out by the free gyro, the gyro has not settled yet on the meridian. Though moving very less as compared to a free gyro, it is still going eastward and westward of the meridian. So we will still need to make some further arrangement to make it point towards the meridian. For that, we will need to analyze the motion of the gyro, behavior of the gyro on the elliptical path. Arising in our mind is that why does the controlled gyro follow a ellipse? Why doesn't it make a small circle, or why doesn't move in a, let us say, square kind of motion or a triangular motion? Why only elliptical motion? And why does the ellipse behave in this way? Why it is so small? Why does the spin axis move back from here? What is the reason? So for this, we will need to understand the balance between the three factors which are affecting our gyro now. These are tilting, drifting, and the control precession generated because of top heavy and bottom heavy arrangement. Let us now try to analyze and understand this elliptical motion of the spin axis. We have now zoomed into the ellipse, the red color ellipse which we saw in the previous slide. It is a zoomed in picture of the same ellipse. Now in this ellipse you can see three different color of arrows. You can see the red color arrow, green color arrow, and the blue color arrow. Now these three arrows represent the three forces under the effect of which the spin axis is tracing this elliptical path. What are these three forces? The first arrow, which is the red one, represents the tilting motion. Tilting motion is caused because the spin axis follows the gyrostar, and as the gyrostar changes its altitude, the tilt of the spin axis also changes. The blue color arrow represents the drifting motion. As the gyrostar changes its azimuth, the spin axis follows the gyrostar and changes its drift, which is shown by the blue color arrow. Blue color arrow is the drifting motion. And the third arrow, which is the green color arrow, represents the control precession. Control precession has been generated by applying the top heavy or bottom heavy arrangement, and it has been included or generated by us to control the free gyro. Now, before we analyze and understand this ellipse in detail, it will be very helpful if we have the formula for tilting, drifting, and control precession refreshed in our mind. It will be better if you have those formulas in front of you, and you can have a look at them when you are understanding. Let me also revise these formulas once again. The three formula which we have seen is number one, the tilting formula, which is 15 degrees sine of azimuth cos of latitude per hour. The tilting is upwards if the spin axis or the gyrostar is east of the meridian, and the tilting is downwards if the spin axis or gyrostar is west of the meridian. It is represented by the red color arrow, so that's why you see a red box around it. Then the second formula was for drifting. Drifting is given by 15 degrees sine of latitude per hour. Drifting is easterly if the spin axis or gyrostar is below the pole. The altitude of the gyrostar or the tilt of the spin axis is less than the altitude of the pole, and the drifting is westerly if the spin axis or gyrostar is above the pole. These are the same formula which we saw when we understood the tilting and the drifting motion. The third force which we have introduced in this controlled gyro is the control precession. And as we saw this in the previous presentation, control precession is directly proportional to tilt. If the tilt is 0, the control precession is 0. As the tilt starts to increase, the control precession also increases. And what is the direction of this control precession? The control precession is westerly the tilt is up. Whenever the spin axis is tilted upwards above the horizon, the control precession will be westerly and the control precession is easterly whenever the tilt is down. So this was discussed when we understood the control precession generation using top heavy and bottom heavy arrangement. So these are the three formulas which should be at the back of your mind while understanding the elliptical motion. It will make your understanding very, very easy. Any doubts up to here? Keep on understanding it one by one. It will keep on getting simplified. Now the approach which we are going to follow is there are three forces which are at play here. Tilting represented by the red arrow, drifting represented by the blue arrow, and the control precession represented by the green arrow. Now we will try to analyze, first of all, we will try to check whether these forces are applied correctly or not. At every point on our ellipse, you can see this is point A of the ellipse, moving on to point B, then C, then delta point on top, then E, echo, F, foxtrot, golf, G, and then coming back to A. So at each and every point, we will be checking whether these forces are applied correctly. And once we understand that these forces, how these forces are applied, how the direction of these vectors, the magnitude of these vectors is put in this diagram, we will be able to easily understand the elliptical motion. So first of all, we go for the drifting force. Drifting is represented by the blue color arrow, and the formula we have just seen, 15 degrees sine of latitude per hour. Now in this particular elliptical motion, we are right now assuming that the observer is not changing its position. If position is same, the latitude will remain the same, and in our formula, if the latitude is same, you will see 15 degrees sine of latitude will be a constant value. Anywhere you go on the ellipse at any of the point, the value of drifting should not change, it should remain the same because there is no variable in the formula. 15 degrees sine of latitude and the latitude is not changing. This is the reason if you take your attention to any point, you have a look at point A, you can see the blue color drifting arrow. You take your attention to point B, you can see the blue color drifting arrow, and you will see that the drifting arrow remains exactly the same. Same magnitude, same direction. You go to point C, the drifting arrow is exactly in the same direction and the same magnitude. You go to point delta, drifting arrow same, echo, foxtrot, golf. At all the points on our ellipse, whether the spin axis is east of the meridian or the spin axis is west of the meridian, whether the spin axis is above the horizon or below the horizon, the value of the drifting vector, magnitude as well as direction does not change, and it fully matches with the formula. Before we proceed ahead, the vertical black line which you see here represents the meridian. You can see the meridian mentioned here along the vertical black line. And this horizontal maroon color line here, horizontal line is the horizon. You can see the horizon mentioned here close to the horizontal line. Point regarding the drifting, you see that at every point the direction of the drifting vector is easterly. Now why is that so? Why is the drifting easterly? Now if you remember the elliptical path and the circular path, I showed you a blue color circle and the red color ellipse. That time I specifically told you that the entire ellipse is made below the pole. The entire ellipse is made below the pole, and we know whenever the spin axis is pointing below the pole, the drifting will always be easterly. So this is the reason why you see the direction of drifting as easterly. So let's move on to the second force in action here. The second force which we are going to discuss now is the tilting motion. Now in this diagram, the red vector represents the tilting. We know that tilting is given by the formula 15 degrees sine of azimuth cos of latitude per hour. As the observer is stationary right now, there is no change in the latitude of the observer, but the azimuth of the spin axis or the drift of the spin axis is changing. At different points, you will see the azimuth is changing. Now we can see that tilting from this formula, we can see that the tilting is directly proportional to the azimuth of the gyrostar or the drift of the spin axis. So as the azimuth increases, the value of tilting will also increase. Magnitude of tilting will also increase. And at the same time, if the azimuth is 0, you see in this formula, sine of 0 will become 0, giving us a 0 tilt. That means when the azimuth is 0, the tilting will be 0. Now let's try to correlate it with the diagram. We have this vertical black line as the meridian. Now when the spin axis is pointing in the meridian, the azimuth is 0. So basically there are 2 points where the azimuth is 0. You have the point Golf and Delta. At both these points, the azimuth of the spin axis is 0, and you can see here that there is no red vector. The azimuth is 0, the tilting is also 0, so there is no red vector at both these points, Golf as well as Delta. Now, as you go away from the meridian, let's say from point Golf, we are moving further on the ellipse. Now the azimuth is increasing. The azimuth of the spin axis keeps on increasing. When the spin axis reaches at point A, it has a certain azimuth. The difference between the meridian and this point A represents the azimuth now. Now, since there is a azimuth present, we will also have the tilting present. And you can see the tilting vector is present here. If you go further away from the meridian, from point A to point B, the azimuth increases still further, and with the azimuth increasing, you can see the tilting vector also increases in magnitude. At point Bravo, the magnitude or the length of the tilting vector is much more. And if you look carefully, Bravo is the point where the spin axis is achieving its maximum easterly azimuth. And you will also see that it is at this particular point that the tilting vector has got the maximum magnitude. After point B, the spin axis moves on to point C here, point Charlie. Now at point Charlie, the azimuth is reducing now because the spin axis is coming back towards the meridian. With the azimuth reducing, the spin axis, with the azimuth reducing, the tilting also reduces. Tilting is directly proportional to azimuth. So tilting also reduces, and you see the tilting vector becoming shorter than what it was at point Bravo. As you go from Charlie to Delta, at point Delta, the azimuth becomes 0. So going from point Charlie to point Delta, as the azimuth keeps coming down, the tilting vector also reduces in magnitude and eventually becomes 0 at point Delta. Now from point Delta, the spin axis moves westwards. So as it moves westward, the westerly azimuth increases now. The maximum westerly azimuth is achieved at point Eco, and you can see here that at point Eco, the magnitude of the tilting vector is also maximum. From point eco, the spin axis, remember always we are considering the quadrantal azimuth here. We are not considering the three-figure notation azimuth. When we discuss about gyro, the azimuth is always considered or referenced in the quadrantal notation. So eco to foxtrot, the azimuth reduces, and you can see that the magnitude of the tilting vector also reduces. Foxtrot to golf, the azimuth comes down, becoming 0 eventually at golf point. So similarly, the tilting also keeps on coming down, reducing, decreasing, and eventually becomes 0 at point golf. So at every point on the ellipse, the magnitude of the tilting vector matches with the magnitude given to us by the formula. Now another thing with the tilting, we are aware that the tilting is upwards east of the meridian. If you refer to the tilting formula, you will see the direction. Tilting is upwards east of the meridian because east of the meridian, all celestial bodies, they rise up in altitude, and tilting is downwards west of the meridian. So if you have a look in the diagram, we have the meridian as this vertical black line. At all the points which are east of the meridian, you see point A, then point B, Bravo, then point C, Charlie. All these 3 points, the tilting vector is upwards. And if you go west of the meridian, you have 2 points in the diagram, point Eco and point Foxtrot. At both these points, the direction of the tilting vector is downwards. So telling us that the magnitude as well as the direction of the tilting vector is correctly shown, displayed in the diagram. The green color vector in the diagram. Now we know that this green vector, which is the control precession, is proportional to tilt. One is that it is proportional to tilt. Second is when the tilt is upwards, the control precession acts westwards. And when the tilt is down, the control precession acts eastwards. Now in this diagram, you see we have the horizon at this particular location. You can follow the laser pointer. This is the horizon. Whenever the spin axis is on the horizon, the tilt is 0. Whenever the spin axis is above the horizon, we have a upward tilt. And whenever the spin axis is below the horizon, we have a downward tilt. So let's try to check this control precession vector starting from point A in the diagram. Now point A in the diagram is exactly on the horizon. That means the tilt is 0. If the tilt is 0, control precession will also be 0. That's why you don't see any green vector at point A. After point A, the spin axis moves along the ellipse and reaches up to point B. Now at point Bravo, we have some upward tilt. Now because of this upward tilt, you see the control precession is now generated. The green arrow is present here, and this control precession is acting in the westerly direction. We know when the tilt is up, the control precession acts westwards. From point B, we move up to point C. Now at point C, the tilt has increased further. As the tilt has increased, you can see the magnitude of the control precession has also increased. The green vector has become bigger. Direction is still westwards because at any point above the horizon with a upward tilt or a positive tilt, the direction of control precession will always be westerly. We move further along the ellipse and we reach to point delta. If you observe carefully, point delta is the highest tilt point in the elliptical path. So maximum tilt is present here at point delta, and you can see that the control precession is also the strongest, having the maximum magnitude anywhere in the ellipse. The maximum magnitude of control precession is also at this point due to the fact that control precession is directly proportional to tilt. Direction is westerly as we are having a upward tilt. Now from point delta, as you move along the ellipse to point echo. At point echo, the tilt has reduced now. Now with the tilt reduced, the magnitude of the control precession also reduces. From point echo, we reach up to point foxtrot. Now this point foxtrot is on the horizon. When the spin axis is pointing on the horizon or in the horizon, the tilt is 0. If the tilt is 0, the control precession will always be 0. It will also be 0. So you don't see any green vector here. The control precession is not present at this particular point. Moving further, when you go from foxtrot to golf. Now golf point is having a downward tilt. Means it is below the horizon. Spin axis is pointing below the horizon. The tilt is down. Now with the tilt down, the control precession is generated now, but it acts in the easterly direction. Because we know from the control precession formula or expression that the control precession acts easterly whenever the tilt is down. You can see the green color vector acting here in the eastward direction. Golf is the only point which is below the horizon in this entire ellipse, and it is the only point where the control precession is acting in the easterly direction. Any doubts, beta? Direction above the horizon and easterly below the horizon. Hence, wherever the spin axis is tilting upwards, the green vector is acting westwards, and when the spin axis is tilted downwards, the green vector for control precession is acting eastwards. So now we have checked the application of all the three forces: the tilting, that is the red vector, drifting, the blue vector, control precession, the green vector. We have checked these vectors at all the points: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf. And we have seen that as per their respective formula, the vectors are applied correctly. Now we will try to combine all this information and we will try to understand why does the spin axis move on an elliptical path. Till now we have seen all the forces individually. Tilting, drifting and control precession all have been seen individually and we have checked the accuracy of these vectors. Now we will try to understand their combined effect and how that effect results in the elliptical motion which we are seeing on the screen right now. So let's start off. When the spin axis is placed horizontal, pointing towards true north, it is at this particular location where the laser pointer is right now. The spin axis is horizontal, so it is pointing in the horizon. The spin axis is pointing northwards, so it is pointing in the meridian. And the point where the laser pointer is right now, this is the point where the spin axis is. So when the spin axis is placed horizontal pointing true north, its position in the ellipse is at this particular point represented by N. Now let us try to analyze the forces acting on the spin axis right now at point N. At point N, tilting will be 0 because tilting is proportional to azimuth. The azimuth right now is 0, spin axis is pointing in the meridian. So azimuth 0, tilting will be 0, there is no red vector. At point N, the control precession will also be 0 because control precession is proportional to tilt. And right now the spin axis at point N is pointing in the horizon. We don't have any tilt, 0 tilt. No upward tilt, no downward tilt, the tilt is 0. If the tilt is 0, the control precession will always be 0. So we don't have any tilting, we don't have any control precession. What about the third force, drifting? Drifting is given by 15° sign of latitude and it is constant all over the ellipse. So at point N also we will have the same drifting vector. So drifting will be present and it will be present in the same direction and magnitude as it is present on all other points. So we will have a easterly drifting Because of this easterly drifting, the spin axis is immediately pushed to east of the meridian. Be careful and pay your attention. As the spin axis moves eastwards, it has come east of the meridian now. That means a easterly azimuth is generated. If a easterly azimuth is generated, the tilting vector is now going to come in the picture. Tilting is proportional to azimuth. So as easterly azimuth is generated, we will have upward tilting. This upward tilting is going to push the spin axis upwards. So it will start to move above the horizon. You can follow the laser pointer. It is moving upwards now because tilting has come into play. Now, as it moves upwards, it is generating some tilt also. As the tilt is generated, control precession will also get generated. And since we have a upward tilt, the control precession will be westerly. So this westerly control precession is becoming stronger and stronger as the spin axis tilt is increasing. The westerly control precession is becoming stronger and stronger as the tilt is increasing. And as the spin axis reaches point B, the control precession has become so strong that it has become equal and opposite to the drifting vector. You see right now at point Bravo where the laser pointer is, drifting is acting easterly. The blue vector represents drifting. Control precession now has become equal and opposite to drifting. Now, since control precession and drifting are equal and opposite, the spin axis will not have any easterly or westerly motion. They will both cancel out each other. At point Bravo, the tilting is maximum. It is the strongest and it is upward tilting. So from point B now, the spin axis moves upwards. It neither goes to east nor goes to west. It moves upwards. Now, as soon as it moves upwards, what is going to happen? As it moves upwards, the tilt is going to increase further. If the tilt increases, control precession is going to become more powerful and it is going to overpower the drifting vector. When the control precession becomes more powerful, it tries to bring back the spin axis towards the meridian. We have a westerly control precession, so it takes the spin axis in the westerly direction towards the meridian. So you see after crossing point B, the spin axis starts to move westwards. Now when it moves westwards, the change what is happening right now is moving westward, the azimuth of the spin axis is reducing. With the azimuth reducing, the tilting is
Sir,
also
no sound.
becoming weaker and weaker. Again at point eco, the easterly drifting and the westerly control precession cancel out each other. The tilting is the strongest here because the azimuth is the maximum. So this westerly maximum azimuth generates maximum downward tilting, and from point eco, the spin axis goes vertically down. As it goes vertically down, the tilt reduces further. With the tilt reducing, control precession also become weaker and weaker. Control precession becoming weaker, the easterly drifting takes over and it starts to push the spin axis towards east. And going like this, the spin axis reaches at point Foxtrot. At point Foxtrot, the tilt is 0. With the tilt 0, control precession is 0, so you don't see any green vector at this point. The only two forces acting now is easterly drifting and the downward tilting. Under the effect of these two, the spin axis goes below the horizon now. You see, drifting is easterly, but the tilting is downwards, so it goes below the horizon. As it goes below the horizon, we have a negative tilt now, a downward tilt, and a downward tilt results in easterly control precession. So as we go below the horizon with a downward tilt, we have easterly precession, we have easterly drifting, and at point Golf, where the laser pointer is right now, you see both these forces, that is drifting as well as control precession, acting in the westerly direction. they quickly pull the spin axis to east of the meridian. So both of these forces, the drifting as well as the control precession acting in the easterly direction, pull the spin axis to east of the meridian. As you go east of the meridian, upward tilting comes into the picture, pushing it upward. So the spin axis reaches back at point A. At point A, there is no control precession. Easterly drifting and upward tilting takes it above the horizon and further eastwards. As it goes above the horizon further eastward, westerly precession is generated, and at point B, the westerly precession becomes equal and opposite to the easterly drifting. So you can see now, under the balance of these three forces, the spin axis starts to trace this elliptical path. As it goes below the horizon here, below point F, it goes below the horizon. We see that easterly drifting and easterly control precession, they are both pulling it in the eastward direction. So the motion from Foxtrot to Golf to Alpha is quite fast, as the easterly drifting and the easterly control precession both are pushing it in the easterly direction. So this explains the easterly motion below the horizon, and we have now seen why does the spin axis move in this elliptical path. Now once it reaches back at A, it keeps on oscillating under the effect of these three forces in this elliptical motion, completing one oscillation in about 84 minutes. We have understood the elliptical motion now. Now the beauty of this elliptical motion is that when the spin axis is moving on this elliptical path, oscillating on this elliptical path, at any particular point, let us say the spin axis was at point Charlie, you try to disturb the spin axis. You apply a force, let us say a upward force you apply, and you take the spin axis to this particular point where the laser pointer is right now, and you leave it here. The beauty of this motion is that as the spin axis moves now under the effect of these three forces, you will see after about 3 oscillations, it is going to come back to the same elliptical path. So wherever you take it, you disturb it and you take it someplace else, it is going to oscillate and come back to the same elliptical path. The same is true if you try to push it inside of the ellipse. Let us say at point C, you apply a downward force, you put the spin axis here. If you put the spin axis here, again you will observe that it will move under the effect of these three forces, and slowly it will go and match with the ellipse, and then it will keep on oscillating where the elliptical path is. So this is basically a stable equilibrium. The spin axis has attained this stability because of the combination of these three forces. The tilting, drifting, and control precession are balanced in such a way that if you try to disturb the spin axis at any point on this ellipse, sooner or later it is going to come back. As soon as you leave it, it is going to come back to this elliptical motion. So this is now called a gravity controlled gyroscope. In short, it is also called a controlled gyro. So in this gravity controlled gyroscope, now we have been able to restrict the circular motion of the spin axis to a much shorter ellipse. However, this gravity controlled gyroscope is still cannot be used as a compass because the axis still does not point along the meridian but keeps on oscillating along the elliptical path repeatedly. It is not settled in the meridian. It is going eastward of the meridian, even though it is coming back, then going westward of the meridian, but still not steady and pointing towards the meridian. So it is still not suitable for our purpose, our use as a direction finding instrument or a gyro compass. Now what we need after this is some form of damping. You see, this is oscillatory motion now. We have a oscillatory motion. Now, one good thing which we have achieved is, irrespective of wherever our gyrostar is, the spin axis is not going to follow the gyrostar. It is going to follow this elliptical motion. The gyrostar has gone out of the picture now. The spin axis is going to follow the elliptical motion, this particular oscillation. And now we need some form of damping so that we can dampen these oscillation and make the axis, the spin axis, settle in equilibrium along the meridian or in the meridian. So some form of damping is required which can dampen these oscillations and make our gyro steady in the meridian. It should settle in equilibrium in the meridian. Now, just to give you a conceptual idea, even though it may not be required for the exams, what will happen to the ellipse if we are in the southern hemisphere? Right now, all along, we have been assuming that the observer is in the northern hemisphere. Now, what if the observer is in the southern hemisphere? Now, in the southern hemisphere, the ellipse is going to look like this. So this diagram, you see the path which will be traced by the controlled gyro in the southern hemisphere. The only difference in the forces which you see here is the difference in drifting vector. The drifting vector is acting in the westerly direction. When you are in the southern hemisphere, the entire ellipse is formed above the pole. And above the pole, the drifting is westerly. So that's why you see the drifting vector, which is the blue color vector, acting in the westerly direction at all the points. So we are not going to go deeper into the explanation in southern hemisphere. You get a question on explaining the controlled gyro, you can easily explain it in the northern hemisphere, and that should do the job. Right, beta? Clear?
Yes. 1 minute.
To see how the elliptical motion of a gravity controlled gyroscope is dampened and how it is converted into a north seeking gyro compass. We have seen earlier that a gravity controlled gyroscope cannot be used as a compass because its axis does not point along the meridian. The axis keeps on oscillating along the ellipse repeatedly. Thus, some form of damping is needed to dampen the oscillations and make the axis settle in equilibrium along the meridian so that we can use it as a direction finding instrument. Now in damping, the controlled ellipse becomes a spiral inwards towards the equilibrium position where the axis is going to settle down, and also what is important to note is that if the axis is disturbed from this settling position, the axis has the capability to return back to the equilibrium position. Now this is achieved by damping the ellipse. This damping is possible in two different ways. The ellipse can be dampened in azimuth or it can be dampened in tilt. Now, the damping in azimuth method is used or employed in bottom heavy gyros. Bottom heavy gyros are the ones which are rotating in a clockwise direction. In azimuth damping, the damping precession, this is the fourth force which will get involved into a damped gyro, north-seeking gyro. It is known as a damping precession, in short known as PD. In a gravity-controlled gyro, we had introduced the control precession, which was known as PC. Now, for damping the ellipse, we will include or introduce a damping precession, which is known as PD. When you use damping in azimuth method in bottom heavy gyros, which are rotating clockwise when viewed from the south end, the damping precession always acts towards the meridian, which basically means that whenever the spin axis goes east or west of the meridian, this damping precession tries to bring the spin axis back into the meridian. So in this case, the damping precession will be either in the easterly direction or the westerly direction. Now the damping in tilt, which is the method used in top heavy gyros. Top heavy gyros are the one which are rotating in the anti-clockwise direction when viewed from the south end. Now in this damping, the damping precession, this is the additional force which we have introduced when we dampen the ellipse. PD acts towards the horizon. It basically means that whenever the spin axis goes above the horizon, the damping precession tries to push it downwards back to the horizon. And whenever the spin axis goes below the horizon, it tries to push the spin axis upwards towards the horizon. So basically, damping in tilt method uses a damping precession which opposes the tilt in all the cases. If you have a upward tilt, it acts downwards, opposite to the tilt. And if you have a downward tilt, it acts upward, opposite to the tilt. Most of the gyro compass made by the makers are anti-clockwise gyros. Viewed from the south end, they are anti-clockwise gyros. So the damping method which is used in those gyros is damping in tilt. So we are going to understand this damping of the gravity controlled gyroscope by using the damping in tilt method. So let's go into the damping of the ellipse by using the damping in tilt method, which is used in top heavy gyros. These are the ones which spin anti-clockwise looking from the south end. So you can see a diagram of the rotor spin axis and the casing. Now in this diagram, the dotted lines which you are seeing, these dotted lines basically represent the rotor. You are looking at the rotor and spin axis arrangement from the south end. This circle in the center of the diagram which you see, it represents the spin axis. The spin axis is going into the screen and it is coming out of the screen towards you. You are looking at the spin axis from the south hand side. So the end of the spin axis which is going into the screen is the north end of the spin axis, and the end of the spin axis which is coming out of the screen towards you is the south end of the spin axis. So we have the spin axis going into the screen and coming out towards you, with the north end into the screen and the south end towards you. So obviously, if the spin axis and the rotor is oriented in this particular way, you will be able to appreciate that in this case, the right side of the diagram will show the easterly direction. It is represented by the alphabet E. So the right side of the direction of the diagram shows the easterly direction, and the left side of the diagram will show the westerly direction. When you are looking at the rotor and the spin axis from the south end, you will be able to see the entire rotor. So the dotted line represent the rotor, and the solid line which you see outside, the solid line represents the rotor casing. Now, as I told you before also, that this rotor casing is connected to the rotor via ball bearings. So the freedom to spin is provided to the rotor and the spin axis by these ball bearings. The casing is not free to spin. The casing, however, is free to tilt up and down, and the casing is free to drift also in the easterly or westerly direction. But the casing is not free to spin. Another important thing, you see the top part of the casing is kept flat. The top part of the casing is flat. So as we have seen that the casing will not be spinning, it is not free to spin. The flat portion on top is going to stay here only. It is not going to spin clockwise or anti-clockwise in any which direction. It is going to stay horizontal and at the top only. Now, when we generated the control precession, we placed a weight exactly on top of the center of the rotor. So we placed a weight where right now the laser pointer is. So the weight was placed here to make it a top heavy gyro. The weight was exactly on top of the center of gravity or the center of the rotor. Now to generate damping precession, we again place a weight on the casing of the gyro compass, but this weight which we are placing now, it is much smaller as compared to the weight which was placed to make it top heavy. In fact, that weight, to be specific, is about 680 grams. And this weight which we are placing now, the weight which is highlighted in yellow color, this is the weight which we are placing now, is much smaller, and it weighs only 17 grams. So the rotor casing carries this small weight, 17 grams on top. It is exactly in the same plane as the rotor. It is in the plane of the rotor, but you can see it is offset slightly to the west of the spin axis. You can see this is the westerly direction, the left side, and the small weight which we are placing is not on top of the rotor, but it is slightly offset to the westerly direction. So this yellow weight which you see on top of the casing, slightly offset to the west, weighing 17 grams, is the weight which we use for generating the damping precession, for damping this in tilt. Which we saw in the earlier slide, it shows the rotor, the spin axis pointing towards you. You are looking at it from the south end, the north end of the spin axis going into the screen. We have the casing represented by the solid black lines, and we have a flat portion on top of the casing. We have a small weight, 17 grams to be precise, fitted on top of the casing in the plane of the rotor, but slightly offset to the westerly direction. Now, this is where the critical part of damping begins. So please pay your attention to understand this particular part. If you understand this one slide, the damping fundamental or the damping principle will be very much clear in your mind. Now let's assume that this particular gyroscope having the spin axis pointing in the north-south direction, the spin axis, because of any reason, let's assume the spin axis starts to tilt. How does it tilt? The north end of the spin axis has started tilting upwards. Now, if the north end goes upwards, obviously the south end of the spin axis will go downwards. Now, let's say it keeps on tilting like this. The north end is tilting upwards and the south end is tilting downwards. Now, if it tilts by 90 degrees and you are looking at it from the same direction, if it tilts by 90 degrees, this is how it is going to appear. You see, this is the spin axis tilted by 90 degrees. The north end of the spin axis, which was initially pointing into the screen, has gone upwards and it will be now pointing vertically upwards. You see, this is pointing vertically upwards now. This is the north end of the spin axis, and the south end, which was initially pointing towards you, it has tilted downwards, and you can see in this diagram the south end is tilted downwards. This is the south end now tilted downwards, and in this condition you will be able to see the top part of the casing. So you are actually looking at the flat portion, the top part of the casing, and this yellow weight which is fitted on top of the casing in the plane of the rotor, this dashed line which you see, the dashed line which you see in the diagram, which I am showing by my laser pointer, basically represents the plane of the rotor. And our weight, the yellow color weight, is fitted in the plane of the rotor and it is slightly offset to west. Okay, you see the spin axis is now vertically up and down, and you can see the weight has been offset to the westerly direction. So this is how the weight is. Now with the spin axis horizontal, that means the first diagram, the damping weight has no effect at all. It does not generate any effect at all because the damping weight is in the same plane as the rotor. It is offset to the west, so it will try to move the western part of the casing downwards, but the western part of the casing it will try to push downwards, but that's not possible because the casing is fixed and not free to spin. The casing is not free to spin, so it is not able to push the westerly side of the casing down. So with the spin axis horizontal, that means the first diagram on the left hand side, the damping weight has no effect at all. But let's assume now that the spin axis has tilted by 90 degrees. That means the second diagram which you see on the right hand side. When the spin axis tilts, the damping weight starts exerting a torque. So if you concentrate on the right hand side diagram, the north end is now pointing upwards and the south end is pointing downwards. The damping weight is offset to the west. So now this damping weight tries to push this part of the casing down. It is basically as if it is trying to push the south end of the spin axis as shown by this arrow. So our damping weight, the yellow color weight, being offset to the west, now tries to push the south end downwards. You see in this particular case, the center of the rotor is here. The left part of the casing becomes heavier because of this weight fitted. The right part of the casing is lighter. So this weight tries to pull down the westerly part of the casing. And if you see its effect on the spin axis, it is trying to push the spin axis in this particular direction. Show it with the arrow. So you can see this arrow appearing on the screen now. This is how the damping weight is trying to push the south end of the spin axis. Now, to understand the effect of this particular force, let me take you to diagram number 1. So we will see how does this force acts on the south end of the spin axis and what does it result into. The spin axis is tilted up and down only, but just to understand the effect of the force, we will now generate or draw this force in the left hand side diagram, diagram number 1, and we will be very easily able to find out there how does this force affect our spin axis. Right now in the right hand side diagram, you see the north end is tilted upwards by 90 degrees and the south end is tilted downwards. And this damping weight is trying to apply a torque or a force on the south end of the spin axis as represented by this arrow. So let's show this in diagram number 1. You can see the arrow in the left hand side diagram. This is how the arrow is trying to push the south end of the spin axis when the north end is tilted upwards. So with the north end tilted upwards, this is how the offset weight or the damping weight is trying to push the south end of our spin axis. Now we know our rotor is spinning in the anti-clockwise direction. Looking from the south end, it is spinning anti-clockwise. So let me show you the direction of the spin and we will be able to then see how does this force actually move the spin axis basis the gyroscopic precession. So this is the direction represented by the maroon color arrow in which our rotor is spinning. It is anti-clockwise direction when viewed from the south end. So now the gyroscopic precession says that this force which is being applied to the south end of the spin axis is turned by 90 degrees in the direction of the spin and will be applied like this. So the force is applied in this particular way now. You see the upward arrow highlighted by the laser pointer. This is how the force gets applied to the south end of the spin axis. So this force tries to push the south end of the spin axis upwards. Now obviously if it is trying to push the south end upwards, the south end goes up and the north end will have to come down. So you can now see that we have generated a force which is trying to bring the north end downwards. So let me repeat it once again. Before the repetition, beta, is it making sense? Now understood the damping precession. Just to summarize, the damping precession PD is proportional to tilt. If there is no tilt, there is no damping precession. As the tilt increases, the damping precession also increases. And the damping precession is downwards whenever the tilt is up. Whenever the spin axis is above the horizon, the damping precession acts downwards and the damping precession is upwards when the tilt is down. Whenever the spin axis is pointing below the horizon or when the tilt is down, the damping precession is acting upwards. So clear beta, this is clear. So beta, these are the four forces now. Three forces we had already seen: tilting, drifting and control precession. अब हमने fourth force को add कर दिया है, which is the damping precession. So if you want, you can take a screenshot of this and keep it pin axis or the gyroscope behave. Now this damping precession converts the ellipse into an inward moving spiral. As you can see in the diagram now, you can see the diagram. There is a spiral motion which is moving inwards. So this inward moving spiral goes in this particular way and eventually settles down at this particular point S. So this is the settling point where the spin axis finally settles down. Now in this diagram, you see four total forces are there, which we just now discussed. That is tilting, drifting, control precession and damping precession. So we have added up only one new force here, which is the damping precession. And we know that the damping precession is proportional to tilt and it is always opposite to the direction in which it is tilted. If the spin axis is tilted upwards, the damping precession is down, and if the spin axis is tilted downwards, the damping precession is up. The spiral path is traced as a result of interaction between these four forces, that is drifting, tilting, control precession and damping precession, ultimately causing the spin axis to settle in equilibrium position. The S position which you see here in the diagram is the equilibrium position. Now right now the diagram looks a bit complicated. A lot of arrows, forces, colors are there, but we will understand this part by part so that it is easy for us to understand. Now beta, if you look carefully, the only new force introduced is the damping precession, that is the yellow color arrow. And if you see, the yellow color arrow is always opposing the tilt. At point Bravo, we have a up tilt, yellow arrow is down. At Charlie, up tilt, yellow arrow is down. At Delta, up tilt, yellow arrow is down. And at Foxtrot, we have a down tilt, it is below the horizon, so the yellow arrow is up. So basically what is happening, it is pushing the elliptical path closer to the horizon, and that results in making it a spiral, and finally it settles down at this particular point. Remaining three forces are exactly the same what we discussed in the elliptical motion. So the yellow arrow dampens the ellipse and converts it into a spiral and settling at position S. So is it making sense, beta? Are you able to understand? I don't think we now need to go in detail from A to B to C to D, all these points. Is it okay?
Yes, sir. Yes, sir. Okay.
This leads the spin axis on an inward spiral, finally making it settle at this point S, where all the four forces, that is tilting, drifting, PC and PD, balance out each other. Now the point where it settles has to be the point where all these four forces cancel out each other. Because if any of the force is not cancelling or not balanced, then there will be some resultant force acting on the spin axis and it will not settle there, it will move to a new location. So it has to settle at a point where all these four forces balance out or cancel each other. This is a stable equilibrium because if you try to move the spin axis out of this position, the forces will get misbalanced, it will get disbalanced, and will guide the spin axis back to the settling position. Let's say, for example, the spin axis has settled here and you apply a additional force in this particular direction and take it somewhere here and leave it. Now, once you leave it here, the balance of all the four forces will get mismatched. It will get disbalanced again. It will start moving on a spiral path like this and eventually come back and settle at this particular location only. So wherever you take and leave the spin axis, it is going to move on a spiral path and then eventually come and settle down at this particular location only. So this basically converts the gravity controlled gyro into a north seeking damped gyro compass, which we can now use on ships as a direction finding instrument. Asked in the examinations also, written as well as orals, why is gyro less effective at higher latitudes? Now, with our understanding of these four forces, we can very easily appreciate why the gyro becomes less effective and almost loses its directive force when we go close to the poles in higher latitudes. You can easily understand it. We have seen in our explanation that the free gyro is controlled by PC, control precession, and is made north-seeking by introducing PD, that is the damping precession. Now both of them, PC as well as PD, are proportional to tilt. That means if there is no tilt, there will be no PC and there will be no PD. Now the tilt is generated by tilting, or you can say the rate at which the tilt is generated is known as tilting, and tilting reduces as we proceed to higher latitudes. Why does it reduce? Let's look into the formula. The tilting formula is 15 degrees sine of azimuth cos of latitude per hour. Now you see, as the latitude increases, cos latitude value becomes lesser and lesser. And at the pole, if you put the latitude as 90, the tilting value becomes 0 because cos 90 is 0. So tilting is maximum at the equator, reduces as we go to higher latitude and becomes 0 at the pole. Now when tilting is 0, that means tilt will not be generated. The rate of change of tilt is 0. That means tilt will not be generated. If tilt is not generated, PC and PD will not be generated. And if PC and PD does not exist or they are not there, the gyro cannot become a north-seeking damped gyro compass.
PC and PD is nil. So we can say that it makes it free gyro again.
Yeah, that's right, beta. With the PC and PD 0, there is no and bottom heavy arrangement. The concept which we have understood, attaching a weight on top of the casing or bottom of the casing and generating the control precession, is very easy to understand using physical weights. But as far as its practical application is concerned, when we actually make a gyro compass, it is very difficult to mechanically generate that effect. Now, an much easier way to generate that effect is by use of a liquid weight. Now, instead of using a solid weight on the casing, what we actually use in making a compass on board is a liquid weight, and it is called as the liquid ballistic or mercury ballistic. We know mercury is a liquid and it's a very heavy liquid. So actually in these gyro compasses, to generate the top heavy or bottom heavy effect, we use the mercury ballastics. So practically the top heavy effect, or if you require the bottom heavy effect, it is generated using a liquid ballastic. Ballastic means something like the ship's ballast, a liquid which we require to put some weight for our advantage, for our benefit. So in this case, we want some weight to be fitted on the casing, and that weight is generated because of mercury. So that is why it is called as mercury ballastic. Now mercury, which is a heavy liquid, is placed in pots which are connected to the rotor casing. These pots are lying in the north-south direction. So let me try to explain it from the diagram. You see the rotor here. It is again the side profile of the rotor. This is the rotor highlighted by the laser pointer right now. And you see the spin axis here. This is the spin axis. And the spin axis is connected with the casing through these ball bearings. You see these two ball bearings, one here and the other one here at the south end. And this dark black line represents the casing. Now what is actually done is, instead of fitting a physical weight, we connect the bottom of the casing to a mercury pot arrangement. You see there is a mercury pot here. Now this particular pot or mercury vessel is having an opening on top. You can open it up from here and fill up the mercury. And this is connected with a tube. You have this connecting tube going at the bottom and is connected to another pot here. One of the ports is on the north end of the spin axis. The other pot is at the south end of the spin axis. So you have this pipe connecting both the pots, and the liquid or mercury can freely flow between one pot to other. It can flow freely from one pot to other. Now this attachment which you see, that is the attachment from the bottom of the casing up to the pot, is not a pipe. It is a solid attachment. Mercury cannot flow towards this side. The mercury only flows in this connecting pipe between the two pots. Now how does this arrangement generate the top heavy effect or the bottom heavy effect? The effect which you see right now on the screen is a top heavy effect. Now imagine that you have a upward tilt of the south end. That means, sorry, upward tilt of the north end. So this is the north end. Let us say the north end is tilted upwards. If the north end is tilted upwards, this is the north pot. The north pot is also going to go up because it is rigidly connected with the casing. The north pot will go up and the south pot is going to go down. Now when the north pot goes up and south pot has gone down, mercury will start to flow from the north pot, which is upward, to the south pot, which is downwards. That's because of gravity. So north pot, which is upwards, now when the spin axis is tilted up, north end of the spin axis is tilted up, mercury starts to flow towards the south pot, which is at the bottom. Now when more amount of mercury is present in the south pot becomes heavy, and this south pot becoming heavy now starts to generate a downwards force acting on the south end of the spin axis. The south pot is heavy, so it generates a downward force on the south end of the spin axis. The same effect was generated in the top heavy arrangement. A downward force was generated on the south end. The gyro was spinning anti-clockwise, seen from the south end, and this generated a westerly precession in the north end of the spin axis. So is that clear, beta?